We are super excited to be here today. This is Tim, I'm Jesper, and we will be talking about Gaussian splatting. And since Gaussian splatting is not a typical Flutter topic, we thought we really start from the beginning. So please take it away, Tim.
Yeah, hi everyone. First, to start things off, we would like to talk a little bit about classical 3D rendering. So let's say we want to render an image of a banana, and we first start with the geometry of a banana, and then we need to add a texture, which someone has to take, and then we apply that texture to the banana, we add a light source and a virtual camera, and we give all of that information to some sort of renderer, and hopefully out comes a nice image of a banana. Wow. This is nice, but it has a few limitations. First of all, to realistically render this banana, we really need to understand the physics of light, and we need to simulate that. And then also, very importantly, it is a lot of manual work to prepare this. So someone needed to model the banana, someone needed to get this texture, apply it, map it onto the banana correctly, and especially, obviously, for larger scenes, this can be a lot of work. So if we have a real banana in the real world, why can't we just start taking pictures of our banana from different perspectives, feed them into something, and then take a virtual camera and get a picture of that banana without doing any manual labor? In computer graphics, this is a concept called novel view synthesis. So what we want is some sort of algorithm that can learn from our images, and then we can query that algorithm for any camera perspective we want and get the image that the scene would look like from that perspective. So how can a machine learn to render an image? What we basically want the machine to do is first do a guess for what it thinks the image would look like. And obviously this guess is going to be terrible in the beginning. And we want to take the difference between that guess and the real image we took, and ideally use that difference somehow to inform the algorithm on how to tune itself to make a better guess on the next iteration. And this is basically a visualization of our error space. And on the left, we can see we want to go to the minimum error possible. And for that, we need to know, or the machine needs to know, which direction to move in, basically which way to improve to get to a better guess. And on the right, basically, if we cannot determine this direction, this is the visualization on the right, the machine doesn't know how to improve. And this is basically, oh, okay, sorry, can I go back once more? So to get this direction, we need to be able to calculate the slope and do something called gradual descent and backpropagation. And those are concepts from machine learning that we don't have time for here. We will show this link at the end as well. But if you want to learn more about those concepts, there's nice talks on YouTube for that. The problem is that most classical rendering algorithms aren't differentiable. So we cannot, the machine doesn't know which way to move in to improve. So we need some new way to represent this rendering so the machine can do that.
All right. So what we basically need is a 3D scene representation which allows us to employ a differentiable render algorithm so that we can use our machine learning tooling in order to create that. So we will try to explain this with this little 3D representation. It's not fully accurate, but I think it allows for an intuitive understanding on how this might work. So the blue box is our Radiance field, and a Radiance field is basically defined by one property, and that is for any point in space, we know the color and the opacity of that point, giving a certain viewing direction. And the other thing, the orange box, that's supposed to be our camera, and our camera tries to render now the Radiance field. So the task is to go from the 3D representation to a 2D texture that we can then actually put on our screens. So the camera is now shooting rays into our volume and in discrete steps samples our Radiance fields. And what we get out of this, you can see here at the bottom, this is basically the representation for one ray. So we walk into our Radiance field, we sample all this, and then if we blend those together, we end up over there on your left side So this is the sensor, so basically what the camera sees. And each pixel that you can see there is basically the blending of all samples from one ray. And if we turn now the camera around the Radiance field, we get an intuitive understanding how we can get from that 3D representation to a 2D representation on the texture. What is also interesting is that we can see that, for example, this pixel now is just green. But if we look at the samples, we can see that the ray penetrates the green ball, then the slate, and also the red ball. But I said that there is something called density in the Radiance field, and the density is used to approximate geometry. And it's basically eating up the opacity that our pixel has. And when that orange curve hits the bottom, our pixel is fully opaque. So anything that comes after that is not visible anymore. And this is also important to keep that in mind. So we need to sample our Radiance field in the right order. So the paper which made this idea really big is called NERV. It's Neural Radiance Fields. It's from Google DeepMind. And what they basically did, they encoded all the information of the Radiance field into a neural network. Really simple one, just a multi-layer perceptron. And what is exciting about this? A, it worked. So this was kind of unexpected. And B, the compression is really amazing. So the weights are actually smaller than the PNGs that were used in order to train the network in the first place. So they have beaten the compression of JPEG, basically. We call this now an implicit representation of the Radiance field because the information of the Radiance field is encoded in the weights of the neural network. And this is also somewhat a problem because if you want to render this now, you need to query your neural network for each pixel multiple times. So 1 million times for a frame. And that makes rendering really, really slow. And that is finally where we come to Gaussian splatting.
So what we want now is basically an explicit representation of our scene so we can render it faster. And this is where something called 3D Gaussian functions come in. On the left, you can see these two colorful blobs, and this is basically a 3D Gaussian function, so you probably all know the Gaussian bell curve. If you rotate that around in 3D a bunch of times, you end up with this. And each of these plots is defined by a few key parameters. And the parameters are basically a 3D position, a 3D rotation, a 3D scale, an opacity, and a color. And these are the values that make up one of these in space. One key thing to note here is that if you look at the one that's purple right now, you can see that it changes color depending on the viewing direction. That is an important part of this that we're sort of going to gloss over because it's quite complicated, but it's going to come into play later again. And now that we have these Gaussian functions, we can basically tell our optimizer that we talked about earlier to find a way to place them in 3D space with these parameters to get closer and closer to the representation of our Radiance field that we looked at earlier. And then we have this Radiance field where our banana is now made up of all of these M&Ms, 3D ellipsoids. And we feed that into some sort of rasterizer and out comes our picture of the banana over time. The cool thing about this is now that this is an explicit representation because what you have to think about is we now just have all of these Gaussians encoded in a file. We can read them out and show them on screen. There's no querying of a neural network, which makes it much larger than the compressed neural network earlier, but it is fast to render, so we can just display it in real time.
So the next few slides will go over how it's actually then implemented in Flutter. The first question is, can you actually use pure Flutter for such a task? And the set answer is no, because Flutter is a 2D engine and you need a lot of 3D tooling. And Flutter don't give you direct access to the GPU. The good news is there is a package around which can help you with that. It's called Angle, which stands for Almost Native Graphic Layer Engine. It's maintained by Google. It's part of Chromium, so it's really well tested, high performant, and it gives you access to the GL context. And with this, what you basically get as a developer is a OpenGL API, and the package on the fly translates your instructions to whatever your platform currently understands. So on MacBook, we get Metal, on Windows, we get DirectX, and so on. There is an existing package for Flutter, and this is how we could start so fast.
Okay, so let's take you through the render journey a little bit. First, basically, we have to read in the file where all of our Gaussian functions are encoded. We skipped over that now because you probably all know how to read a binary file. But then we somehow need to prepare all of these Gaussian functions that we have for the GPU. And a really efficient way to pass a lot of data to a GPU is to write it into a texture that the GPU can read. So we encode each of these Gaussian functions in 5 texels, which is a texture pixel. The first one encodes the XYZ position as well as the quaternion that represents the rotation. The second green pixel here encodes the 3D scale as well as the color and opacity. And then the 3 blue pixels encode the spherical harmonics, and that is basically the magical part that I glossed over earlier. So this is the math that makes the Gaussian function know which color to take on depending on viewing direction. And again, we're going to skip over this, also partly because we don't understand the maths ourselves. But yeah, then this is basically how we send all this data over to the GPU.
All right, so we are still on the CPU. The next step that we need to do is to sort our Gaussians. And you have seen this in 3D space, right? If our Gaussians are not sorted in the right way, then we will get the wrong color for each pixel. And the sorting is just in an isolate, it's a Radiance sort. And we do it, of course, depending on the camera perspective. So when the camera moves, then of course another Gaussian is the nearest to the camera, and then you have to resort. So now we basically have all the ingredients ready, and we can hand them over to the GPU. This is a GPU, if you wonder. So one thing is the texture, which encodes all the information about our Gaussians. This little notebook reflects our order. And the camera is standing for the intrinsic and extrinsic properties of our camera. And what we want the graphic card to do is to render a 3D model. This is the little car. So the first thing we need to do, we need to set the pipeline of the renderer. We turn off depth testing because we basically take it over by ourselves with our order texture. And then we set up the right blending so that we can blend our Gaussians in a way that they end up as a correct pixel. And the next few things are basically just the uploading I already described. So, and from there, we hand this over, and the first thing that gets into action is the Vertex shader.
So now we're finally on the GPU. The Vertex shader is the first thing that runs in an OpenGL graphics pipeline. And this has a really important part in the whole journey, and this is basically what the term splatting in Gaussian splatting refers to. And you can conceptualize this by the Vertex shader taking each of those Gaussians from our file and throwing them against the camera lens and seeing where this Gaussian 3D ellipsoid splats on the camera as a 2D ellipsis. So what this does now, it runs 4 times per Gaussian to create 4 vertices. And you can sort of see that on our AI-generated image. You have a rectangle for each of these ellipses that perfectly encapsulates it. And these 4 points are found by the Vertex shader by projecting this 3D Gaussian onto our camera lens. And what it also does down here is calculate the color, both from the base color and opacity, as well as the spherical harmonic stuff, and then gives this color to each of the 4 vertices to use later in the pipeline.
All right, so now we have that square, which basically perfectly encapsulates one of our ellipses. And we hand that over to the rasterizer, and the rasterizer basically checks which pixels on screen are inside of that square. And then for each pixel, it takes that pixel and hands it over to the fragment shader. And at that point, we actually don't call them pixels because it's more like a pixel candidate, and we have seen that in 3D, right? Many pixel candidates will make up the final color of the pixel, and that's why they are called fragments. So what the fragment shader does now, and you have also seen this in the 3D representation of the Gaussians, they had these blurry edges. And this is what the fragment shader is now adding. And it's basically just a circular alpha fall off. So we just fade out to the edges. All right, and if you put this all together, then you get a rendering like this. So we had a toy car in the office. That's the toy car. And there are a few interesting things. So the whole thing is fully composable with Flutter. So you can have widgets in front, you can have widgets in the background, and you can really integrate that 3D view into your app. Also, you remember spherical harmonics, so the view-dependent color. This is, for example, used here to create these reflections in the window. And also interesting, because it's hard to take photos from the bottom of an object, during optimization, we didn't have data of the bottom of the car, right? But it's actually beneficial right now because we can see the Gaussians. So the ellipsoids that you see here, which are basically stretched into those spikes, this is actually the thing we were talking about the whole time. So this is a splatted Gaussian.
And you can also really see that well if you closely zoom into the, ooh, not that close. Like you can sort of, it's difficult to control. You can sort of see those here in the texture on the side as well. So this is something you can start to conceptualize in your mind. So now you saw this and you're probably all wondering, how do I try this myself? This is so cool. So the first thing you do is basically you take an object that you want to represent as a Gaussian splat and you start collecting data. So you can take a video, you can take a bunch of photos from around it. You don't need that many actually. And then we need to first figure out the camera positions for the computer to know where those pictures were taken from. And there's an open source tool that we recommend for this. It's called COLMAP. And it runs in your command line. And what comes out of it is basically what we see here represented in Blender. We see a camera position and a sparse point cloud that gives the optimizer a rough idea of the layout of your scene to start off with. And then this data, together with your images, you feed into a training algorithm that then starts optimizing on it to, you can sort of see it here in the video, represent your scene as a Gaussian splat. And there's many tools for this, but the one we would recommend is called Brush. And the good thing about it is it doesn't depend on TensorFlow, so it runs on all platforms, and it's also open source, and we have links at the end for it.
All right, so the last 2 minutes we want to spend on, let's call it Gaussian splatting in the wild. So I found this app online and I liked the idea. So what they basically did, they offer restaurants a 3D menu of their dishes. And it really fits well with Gaussian splatting because a restaurant can just scan their actual dishes, so there is no need for a 3D library or so. And due to the really good visuals of Gaussian splatting, you can actually see your food, right? Low poly food just doesn't make really sense.
And another good use case is, of course, AR and VR, especially for putting real objects into your scene, like this cat, or also for museums, because you can just capture a real art piece and then put it in your virtual museum, and all the textures are represented quite well. And also stuff like fine details, like hair on the cat. Gaussian splatting is way better at representing that efficiently than traditional render algorithms.
So in the last example is Google Maps, and this is just to point out that there is Gaussian splatting already in the wild and it's widely adopted. So Google Maps has this feature called immersive view, and you can basically check out a place before going there. And you can actually do this right now in Google Maps. I mean, there are not many spaces which are already tracked, but mainly in San Francisco, you can find some restaurants that you can visit virtually in Google Maps. So, and this basically concludes our talk. So in our opinion, Gaussian splatting is here to stay. It will live alongside traditional 3D rendering because there are also a few downsides. For example, rigging and animation is way harder in Gaussian splatting than in a normal 3D engine. But there are also these benefits, and so we think it is a really interesting technology for the future. Thank you.